Hey everyone, so here's the second video on just intro to more data manipulation via Tidyverse. So I'm going to talk about basically you have some data set you downloaded or were given to you by a stakeholder. How do you take that data set, clean it up, and get it into form so then you can start to analyze it and build statistical models or visualizations from them? And so I think the easiest way and increasingly becoming the norm in the R community is to use a lot of the packages um, built around the Tidyverse. And so, and just like before I really get into it, a lot of the stuff I'm talking about, the transformation, tidy, and importing data, all of that, and we'll talk about later, visualizations and modeling can all be found at this book, R for Data Science. It's a really good intro to R. It was written by the person who wrote a lot of these packages that we're talking about, Hadley Wickham. So the vast majority of the time when you are kind of working with data in R, it kind of follows this kind of pipeline. So first you have to import the raw data that you have. You have to somehow get it into the right structure. You have to tidy it up. And then you're kind of in this kind of loop where you're transforming, you're kind of manipulating it, creating some plots, you're visualizing it, you're creating some models, and then going back and forth. And as I mentioned, like in the other video, this is like this kind of circle is kind of what they were imagining when they were coming up with the programming language. You're kind of going back and forth between transforming the data, visualizing it, modeling, etc. And then in the end, right, you communicate it to other people. But the one thing I want to highlight is that when you take like most other stat courses, or most of the time when you're learning R at a university, they spend the vast majority of the time, they're like, okay, here, we'll teach you how to import it into R. So you have your data set. We'll teach you some quick like plots, how to make plots, and we'll teach you how to build some like linear models, etc. Which is great. I mean, these are all like important skills in this pipeline, but the other kind of components usually get forgotten about. How do you tidy your data set so it's usable in like a lot of analyses, and how do you also manipulate it? How do you transform it? And because a lot of times too, when you get these data sets from stakeholders, they're not clean and easily workable data. They usually informs you need to do a lot of coding to clean it up. And so what I'm going to try to focus on is trying to get these kind of other avenues that you might have missed already. But if you also are just totally new to R, we will get more into the visualization and modeling later on too. So don't worry, that part will be covered. But today I'm just going to focus on these two, the tidy and transforming. So just before we get into it, what is a Tidyverse? So Tidyverse is this collection of packages maintained, I think virtually all besides one, I can't remember if it's string R, but virtually all these are maintained by RStudio. And this is basically to solve all those problems in your kind of pipeline of getting data and then getting down to communicating it. There's all these packages that work well together that make kind of data manipulation and kind of working in R really easy. So you can read in data with like read Excel. If you have Excel files, read R. Okay, McGreer is, I can never pronounce it, but this one, the piping one, is not part of Tidyverse, I guess technically, but it's heavily used in Tidyverse. And so like you can read it in, tidyr allows you to work with your data frames, get it into the right form. Piping with the McGreer is super helpful for gluing everything together. dplyr is this package that allows you to really manipulate data sets. And we're going to focus a lot of time today on that. You probably have all heard of ggplot. It's a very popular package. In my experience, I feel like most people most people from other stats backgrounds cover ggplot pretty well. And I think in R Markdown too will get covered, but most of the other packages are usually avoided. And I think dplyr in particular is one that they cover somewhat, but it's really vital for data analysis. So there's all these cool packages, they work really well together, and I think it's the simplest and most effective way to approach R. And Tidyverse is kind of built around these kind of four like guiding principles. First, The code is meant to be human-centered. So it's supposed to be really easy to read and helpful for people writing the code too. It has consistent forms. So virtually all the objects in Tidyverse all kind of written the same exact way. So once you learn one package in it, it makes it really easy to expand to others. It's composable. So basically, there's a lot of times in R, you're trying to do these really complex operations, but once you know kind of the 4 or 5 pieces that can go into to solve that, it makes it so much simpler. And kind of building or playing with data with like Tidyverse and especially dplyr, it's kind of like more, I want to say like Lego, like playing with like Legos, where it's like there's specific, you only have a few pieces, but once you get really good at them, you know how they fit together and you can make really cool stuff. And then like I was mentioning before, it's inclusive because the packages all work together, but also, and probably most importantly, there's a growing community of people who use them. So you'll find that a lot of the help forums are now shifting to a lot more Tidyverse. And for like the vast majority of uses, I think the Tidyverse is probably the way to go. If you're trying to do more production code, maybe you need something faster like data.table. But for the vast majority of stuff you all will be working on, Tidyverse is really helpful. And I think for beginners, it also simplifies stuff because in a lot of times, base R gives you like 50 different ways to do things, albeit Tidyverse does too to some degree. But I think it's really confusing because a lot of it's just not readable and there's like a million different ways to do the same operation. So I think Tidyverse kind of streamlines that kind of process for you. So just an outline of what we're going to cover today. First, I'm going to kind of talk about the main functions, or as they refer to them in dplyr as verbs, because they kind of do something. We'll talk about the dplyr for data manipulation. We'll talk about piping, which might not seem really, at first might not seem very interesting, but it's really powerful. Then we'll talk about some of the more summarizing functions you can do with dplyr. Then we'll talk a lot more about how to join different data frames. And then pivoting data too, we'll talk about tidyr a bit. And then at the very end, I'll give this other example that hopefully will tie in all of these together and solidify these concepts. So first, let's dive into dplyr. So dplyr is built around these kind of fundamental key functions, or they call verbs. And virtually every dplyr has a lot of other stuff in it too, but these are the most common by far of what you'll use. So dplyr, just to back up a little bit, dplyr only works with data frames. It's built around working and manipulating data frames. So you need to make sure your object you're trying to work with is a data frame. And then you can kind of work from there. So first one is select. And select is really useful to actually pick out specific columns you want. So you select and then you kind of list off, or so you just write out the different columns you want. And then you can take this data frame and then you'll kind of subset it to those columns. So this blue columns are the only ones that remain. So that's like working off the columns. If you're doing rows, then you're going to be working with filter. So filter allows you to choose which rows in your data set you want to keep based off some kind of conditional statement. And so filter is actually very much the same if you're used to Excel, and if you use the filter command, it's like imagine you select the whole data set in Excel, and then you hit filter, and then you clicked one column, and then say you set like column X needs to be greater than 50, and then it'll only return those rows. It's the same exact idea here. So you can filter data sets. So for select and filter, you're kind of taking your bigger data set and you're whittling it down either by the columns or the rows. Arrange allows you to organize the rows in a specific order based off one or more columns. I believe I virtually only use one column. Actually, you can use two, not totally certain. Anyway, so that one's not as commonly used, but it can be useful. We'll talk about summarize later, but it's a way to take your big table and get some like kind of summary statistics or distill it down to a smaller table. The other really important one is mutate. And mutate allows you to create new columns. And so it allows you to basically either do some kind of calculation based off the other columns, or usually based off something existing in your data set. And then we'll talk about group by later, but group by is extremely powerful too, and probably one of the biggest upsides of using dplyr, because it's trickier to use group by in other contexts. And so just to kind of give you an idea of what these kind of objects can do, or sorry, the verbs can do. So all of them are set up in this form where it's like some kind of functions, either it's filter, select, mutate, etc. And first you plug in your data frame. So this is your .data command, or sorry, argument. And then there's a ... basically means then you plug in something else that's specific to that function. So imagine we have this data set called dat, where there's an X column and a Y column. There's just a bunch of numbers. And so from this, you can say use the filter command. And then so you first plug in your data frame dat, comma, because it separate the arguments. And then you select, you choose a column, say we want only the rows where X is greater than 100. And this is not a great example because I should have done Y, because it wouldn't return anything because there's no columns where it's 100. But imagine this was Y, it would only return this row here. And since that's the only one that meets that condition. And so I'll show you later, there's a full table of all the different kind of symbols you can use. It can be greater than, less than. You can also do greater than or equal by adding equal sign after it. But there's also a few others that are really powerful. So that's how you filter it. Say you only wanted to return that X column, you can do dat and then just write the column X, and that'll just return you this X column here. Imagine you wanted to square everything and create a new column. So if you use mutate, then you name your new column X_2 equals, and then so when you're creating mutate, you always put an equal sign here. And then X squared means we're trying to take this column X and square everything in it. So then we'll have like 1, 4, 9, 16, 25 here, and it'll be X squared on the furthest to the right. Furthermore, you can also create another column. I call them calc, where we can just also divide everything X divided by Y, and it'll create a new column to the right too called calc. So just as I mentioned, like in the philosophy, all of these they have the same kind of structure of the function. So it's your data first, and then what you're doing to it. What's like your specific ask using that kind of verb. So now let's go through some examples, and I'm going to use this cool data set called the Polymer penguins. So it's a bunch of measurements of penguins down in Antarctica, I think by the Polymer Station, I believe. And it's a really nice, useful data set for these kind of operations. So I'm just going to open up my R window. One thing, sorry, I apologize, I didn't mention this in the other class. But very important is that whenever you see these pound signs or hashtags or octothorpes or whatever you want to call them, this is a comment. And so if you run this, it's not going to do anything in R. So I apologize, I forgot this last time. So it's helpful just to comment your code so you know what's happening and so what each of these things do. So first thing we're going to do is, if you haven't installed Tidyverse, run this line of code first. It will install that package for you. You can also do it here if you want to, just install it here. Either way, install Tidyverse. I'm not going to do it because I already have it all installed, and it can take a while to update the very minor updates they have done on some of those packages. And so let's just load in Tidyverse. Tidyverse is loaded into my computer now. We should have it up and running. And then next, the data set for the penguins is actually available too on CRAN, so you can just download it here, I believe. If not, it's also available on GitHub, and if you just Google Polymer penguins, oops. Pull up this data set here, and you can download it via this link here if you run this line. Make sure if you don't have remotes already, run this remotes command first, but then it should download it for you. Anyways, so if you run this, should download the data. And then you should be able to access it. So I can just run help sign, pull it up, because I can't remember exactly which the data set's called. But if you go down here, you can see index. It'll give you all the different functions within it. So there's just a path to file where you can get the raw data, but we're going to rely on this penguins data set, which is just loaded in. It's called penguins. And they give you size measurements for adults foraging penguins near Palmer Station in Antarctica, with 344 rows and 8 variables. So we can just quickly view the data set. Sorry, let me hide this one. You can just run, oops, I not load this properly. No. Should load in the data set. Oh, that's because I wrote Palmer penguins as opposed to open. So you can see here, here's the whole data set's tibble, which is just a fancy data frame essentially. And it gives you that these are all factors for the species. Here's the bill length, bill depth. These are double, so numbers with floating points, integers, factors, and year. And we can open it through view to get like a prettier view of this. You can see all the data here. So you can see there is some missing data in this data set. It's not perfect, but here's kind of what you're looking at. It's set up in the right way, in which we'll talk about later, which makes it easier. This is called long form data. So every observation is a row. And so you can see here we have some categorical stuff like species and islands and sex, and that these can be then selected, or we can use filter for them, and also some numeric values. So now just going through some dplyr examples. So we can look at the filter object. Let me pull up the help file for that. We want the dplyr version because there's also a stats one. And so there's a bunch of different helpful commands with dplyr. So the double equal sign means it has to be exactly that. It's equivalent to. Yeah, here's a greater than for equals. I'll run through some of these. It's might not seem super helpful yet, but it makes it easier. So if I'm running this command filter, right, we first plug in our data set, which is penguins in this example. Penguins is this one here. It was loaded in from the Palmer penguins data set or package. And then we then specify which column we're going to do some conditional filtering on. And so we're going to say we want to look at species and we want to look at Gen 2 penguins. And so this is saying that double equals say return only the rows where if species is equal to Gen 2. Or in the species column, the value there is Gen 2. So since there's a deli, these rows are all going to be discarded, and we're only going to get the rows back that say Gen 2. So you can see it's a smaller data set. I'll pull up so you can read both at the same time, where this is like 10 rows plus 334, so 344, versus this one now is only 124. So that's just filtering out just the Gen 2s. And you can do much more complex operations within the same line. You can say we want species to equal Gen 2, or we can say we want species equal to GenStrat. So we can pull up both of these at the same. We can get rows where they meet either of these two conditions. And we do this by putting in this OR symbol here. So the bar sign here, which you can find on Macs if you do Shift and the key right below the delete button, that'll give you this OR. So one of these two conditions must be met for it to return that row. So you can run this, we'll get more data because now we're kind of including GenStrats within it. Another way you can kind of do this is using this in operator. So you can say species in, and it's basically saying when you have your species column, it must match anything within this vector. And this is really powerful, like, because if you know you have like 5 or 6 conditions, it can be a pain to put OR a million times. Instead, the in operator is super helpful. So it's saying like any of them in this vector. Besides that, you can do more complex filtering at the same time. So then you can say, so we have our penguin data set still, we're going to pull out the Gen 2s, but then we're going to also specify with this and that they have to be Gen 2s and females. And so we get specify different column sex here, and then we can filter both of those at the same time. And so you can see now they're all Gen 2s, but now they all say female too, because we removed all the males, whereas before, right here, when we just ran Gen 2, we have male and female. So right off the bat, you can kind of parse that down to a much smaller and specified data set pretty quickly. So that's the filter, probably the most useful one. Next is select. So select allows you to choose which columns you want. And then for these, just kind of like with these, you don't need quotations or anything, you just write the column names. So I'm going to say I want to only return the columns that are species, sex, and body mass in grams. So you just run select, and it'll be a much smaller data set of just species, sex, and body mass. So if you watch the other video, remember where I was showing you how to subset using the bracket notation, it can be kind of a pain because you would have to figure out which index they're all in all those and then plug those in. So this is much more readable, much easier to operate. Next down the list, let's create a new column called build depth length prop or proportion. And so I'm going to take it where I'll take the build depth and divide it by the length. And so you can also create a new column pretty easily with mutate here. And then it's just going to do the math where this is going to, all the values of the build depth will be divided by the build length for each row. So you run this. And sometimes with dplyr, if it'll relegate some of the columns to the furthest right off screen. So you can see here it says 334 more rows and one variable here. And this is that new variable you're creating, which is not super helpful, but you can just rerun it by pulling that out and we can see that variable here created. Also, right, we could also view it. And since this isn't a saved object like the penguins, it's going to come up, I believe, as, yeah, just a command we ran here, which is fine. But it opens as a different tab because of that. So here, yeah, you can see the proportion bills. And view, you can sort stuff really easily. Super cool. Okay, so that's like kind of the basics of dplyr. They might not seem super powerful yet, but it makes life so much easier just to use those few commands. So going back to the data set, what I also recommend is that RStudio has a bunch of these cheat sheets that they create. And so these cheat sheets are super helpful because they basically show you the commands and little diagrams of what they do. And so it's a really helpful way to get a sense of other stuff haven't showed you yet, but the power with it. And I think like, especially if you're starting off with starting off with like dplyr, this is a really helpful tool to use to make sure you know what can be done. Because there's a lot I didn't cover yet, but it should clarify a lot of it. But yeah, cheat sheet, super helpful. I'll put a link in the video description at the end. Okay, next up, let's talk about the pipe. So the pipe is this operation. It's created by using the symbols here of the percent and the greater than, I can never remember which one, whatever that sign is, and then another percent. And by doing this, what's really helpful about this is that it allows you to string together a bunch of these dplyr verbs to create like a pipeline within your script. And so the way you read this is that if you had some x piped to f, it's equivalent to saying like f of x. So this, you're doing some function of f to this x. And so the way the piping really works is that so you know, as I was saying earlier, right, your first argument is always data. And then after that, you're doing something to that data in dplyr. What dplyr is set up that way specifically to work really well with piping. And so what you do is that you can pipe data sets into functions, or sorry, verbs like filter, and then it'll do that command to that, and then you'll have an output with that filter data set. Makes it really much more readable too. But because all the verbs are set up that same way, you can take the output, say, of this penguin and filtering by that bill length, and then string together 3 or 4 more filters or mutates, etc. And this allows you to take these very simple composable operations that we're using and build a really complex pipeline or kind of specific manipulation. And so like, even though you're not learning that many tools, so some like dplyr sounds somewhat underwhelming at first, but it's super simple to use and allows you to build something super customizable. And it's extremely easy to read too. And so the pipe is kind of this glue to take the outputs from one function to the next, and to the next, and allow you to build these really cool outputs. And so and a way to think about the pipe is to think of it kind of like the word then. So imagine you have imagine you're trying to build something like this where you have some data set called YDAT, and then you're trying to filter out for some specific genes, leucine, biosynthesis pathway, et cetera. So you want only these genes, that gene specifically. And then we haven't talked about group by yet, but you want to then group each of these elements together and then calculate correlations with their expression. And then you want to round those kind of correlations to 2 digits, and then you want to arrange it so that the rounded correlations are organized. So it's very straightforward of like what you would want to do step by step. If you were to kind of write this with dplyr, but with the old code, it would look something like this, which is impossible to read. And the problem with like BaseR in particular is you have to go from the most inward parentheses and go out, kind of like if it's nested or kind of like shaped like an onion or something like that. And it's really hard to read unless you know exactly which parentheses you're in. It's not human readable at all. And so as opposed to like now if you use dplyr with piping, right? It's the same exact thing. It's kind of this paragraph you read before, but now just in code. So now you're just replacing the thens with the pipe. And then here's the commands filter. So the gene leucine biosynthesis equals means we're only pulling out that gene. We'll talk about group by in a second, summarize, but yeah, it's a much easier way to read it, and allows you, and nice thing too is it's very linear too. You know, YDAT's going into this pipeline, and this is like the last thing you're getting out is this arranged R from all these other steps. So it makes it code super simple to read too. Okay, let me go back to the PowerPoint. No, not PowerPoint, sorry, R. And show you kind of how piping works. So, right, you can just show you before, right, we can just pipe in the penguin data set into it. Because remember, the first argument is always assumed by the pipe as the .data, so everything links up well. So run that. You can pipe it in. So saying we're taking the penguin data set, then we're filtering species to Gentoo and sex equals female to get this data set. So it's equivalent to just plugging this in here, but now this is much more useful. And one thing too, you'll notice if you read a lot of scripts from BaseR, you'll find that a lot of times people end up with all these intermediate objects they create because they're doing some big operation. And it's really only a placeholder because they're trying to split up this really complicated pipeline. And so that's fine. There's nothing wrong with doing that, but it can be hard to read the code too, because then you're trying to figure out, is that intermediate like actually important, or is it just something to build, it's just a means for something else. So you don't really have to worry about that much. And so kind of the convention too, right, is that you can also, and for dplyr, is that you can also say, take this kind of pipeline, where we're going, this time we're just selecting the island and bill length after we pull out the Gentoo and females. And you can also just quickly at the very top, you can just assign it to penguin smaller. So I can run this whole thing here. And just click this, you can click the top line and I'll run the whole thing for you. And then we just create this penguin smaller data set pretty quickly. So it's easy to read with penguin smaller, and then the assignment arrow, so right, we're assigning everything below it to this new object penguin smaller. By convention, another thing I forgot to mention is that you want to start the first one without an index without being tabbed. And then everything below it should be one tab below that. So it's kind of, this is like the very first thing you did, and this is everything corresponding to it. You can also be fancier too, and if you tab like this, you can build this so it's on more lines. I don't find this necessarily as readable always, but it is something that is common. Cool. So this is how you can string together multiple filters and multiple selects. And then so like just to show you kind of this kind of pipeline of how complicated it can get, and just I think generally readable. So let's take that penguin data set again. And then we're going to filter so it only includes the year 2007. Then we're going to only select species, island, build, depth as our columns. So I can kind of show you step by step what this looks like. So right, only 2007. Then we're going to select those columns. Species, island, build, depth. This is a command and built in with dplyr. It's also helpful. So if there's ever an NA, it will remove that whole row. Be super careful with this, that you're not removing, that you don't have some other column where it's all NA, so you'll lose a lot of data. I'm just doing this simply just to show you that it is a function that's part of it. And so when you specify it with this, I'm only removing NAs from the build depth millimeter, but drop NA is helpful too. So it's going to remove, say, that fourth row here. Oh, what did I do wrong? I didn't include the data, so I got messed up. So you can see I dropped a few rows. Then I can create a new column, or I'm just going to make it centimeters. And I haven't mentioned this yet, but for select to, if you want to remove columns, it's somewhat similar to indexing or subsetting in base R, where you can just use a minus sign for that column and it'll drop that column for you. So the millimeter column will now go away when I run it with that select. Awesome. So just quickly just showing you that like you string together a few filter selects, mutates, and you can get some very specific data set or very specific data frame that then you could say you plug into ggplot to create a plot for it, or say model something specifically. But then let's now go more into like kind of creating summaries. So I think my PowerPoint's out of order. Or did I not create a slide for it? Oops, sorry. I did not create a slide for it. So I'll just go over it quickly. So for summaries, you can actually then calculate some kind of variable across each of these rows and get like a smaller table. So easiest way to think about this is to say like, what if you wanted to find the mean of all the, I don't know, I want to look at the average body size of all these different penguins or different species of penguins. And one of the very helpful functions, especially with summary, it doesn't have to be with summary, but often is this function called group by. And group by basically takes your whole data set and then it kind of parses it based off whatever columns you chose into like smaller data sets where they're kind of specified by that species. So what I mean by that is you're grouping by some categorical variable, and it kind of is creating sub data frames based off whatever is in that species. So, right, the species, we have the Adelie, the gentooth, the chin trap. It'll create 3 separate data frames for those. So if I run this command, you can kind of see it too. It'll say the groups here, and you can see all the groups will be organized within that. Now, this doesn't mean, this is like kind of more of an internal detail, but it allows you to do really cool things because it allows you then to say calculate the mean of each of those penguins at once. And so you can add many groupings. You can say, so right now if I calculate the mean, it's going to say Adelie penguin's mass is X, chin strap is Y, etc. But it say I could also then add island too. And then it'll break it up by penguin species and the specific island. And so then you can calculate these summary stats really quickly. So penguin, and so I'll just show you this kind of pipeline where we calculate average body mass and throw in some other summary stats really quickly. So the only variables we really need, right, is species, sex, and body size. So I'm just gonna trim our data set down and make it simpler for now. So you can see Adele, see male, body size too. I'm going to include the drop NA. So it's going to look for any NAs in the data set and drop those rows. Just for simplicity now, I wouldn't recommend this in the future. I would actually investigate those rows closely. And so now we're going to group by species and sex. So we're basically going to say, create all the groupings of the different males and different sexes and the different species, and create kind of partitions for in the data set. And so you can also see, it'll tell you the groups. So say we're grouping it by species and grouping it by sex. There's 6 different ones, right? So it'd be 6 different groupings that's calculating. And then for summarize, then by using those groupings, then you can use a functions, for example, like mean, so calculate the average of some specific column, and it'll calculate the mean body size for each of those groupings, which is super, super cool. Same thing, I create like a standard error where it's just like standard deviation by square root, and just it counts the number of rows within each of those groupings, and then number of samples n, so error number of samples. So if we run all this together, it just basically gives you kind of the data you might need to create a figure looking at the different masses of the penguins and partitioned by sex, and also say have your standard error and number of samples if you're interested too. So just like that, we can just create like a pretty cool summary, and then you can save it to an object. And the last thing I want to say is whenever you do a grouping and you're going to use this data set further, always run ungroup. Remove that grouping, because sometimes if you're running mutate later, you might be mutating and computing new columns based off those groupings, and often you don't want that to happen. That's a very, very common error with dplyr, and most of the time people have problems. They forgot to ungroup after they did some kind of group by operation. So we run this, we can just save this whole data set. And then summarize will tell you the groupings, which is fine. The errors often are common. And so you can also view it here in the table view. And so you can also group by. Another fancy function along with group by is you can do add counts, and that'll just tell you how many rows meet each of those kind of specific groupings. So like when you group by like multiple variables, it gets to be very, very specific quickly. So, right, we can look at penguins and species, island, and sex. And you can see we have 13 groups right now. So it would be one group is like Adele Torgerson, because that's the island, and male. Another group is Adele Torgerson, female, etc. I mean, we can get even more. You can add, say, year, and you can get even more specific. We'll get much bigger, so 35 different ones. One command that's really helpful is you can do add counts, and that'll add how many rows meet each of those conditions. And so then I can tell you how common that kind of grouping is. Now, keep in mind, right, that this is still the long form data set. This is a full data set. I didn't summarize it yet. So then you don't see each of those groupings only once. You see them all fleshed out with their individual values for each of them. So it's a saying that for Adele Torgerson male, there are 7 kind of observations that meet that. Oh, from 2007 as well. And so you can see there's not that many are Adele Torgerson, where they're NAs for sex. There's 5 of them too. So add count's helpful too. Let me think. What last one? This is just more specific and just to show you kind of if you threw an island in year 2, right? Now, when you do summarize, right, it's going to show you all the permutations of species, sex, island, year here. So species, sex, island, and year. And then the average mass is what we're calculating by doing mean for each of those. So that's kind of how summary works. It's really helpful. I use it a fair amount for just making sure I have all my samples in the data set I want. It's a good way to tally and see if you're missing data, if you know how many you're expecting. many samples. It's helpful to create new variables too with this. So it's generally super helpful. So next we're going to talk about join by. I'll jump back to the PowerPoint for this. So what if you say you had multiple data sets and you wanted to merge them into one bigger data frame so that then you could use like kind of the power of like row by operations to see what's happening. And say, because like I guess the best example I can think of is often I have some data set with values, say like looking at stream quality. And you also have some metadata where it's like you have data from each of those sites and you want to kind of match those up so you can do some kind of regression looking at, say, temperature and some kind of stream quality metric. And so you probably have those in two separate files in two separate places, and you want to get them into one kind of data frame. So dplyr joins are super helpful for that. And so how they work is basically you have these two data sets and you have some column that they share. So that column can either be like the stream example, if there's some kind of site, like you have, I don't know, the name of the town, then you can group those two and then you can match them up. And then dplyr allows you a bunch of different forms where you can either join based off one of the two data sets and determine what you want to do if there's missing data in either of them. The vast majority of the time, you'll be using left join, full join, mostly left join and full join. So left join basically means, say you have some data set X and you're grouping it or you're merging it by some column, say it's town in the example. And your other metadata, imagine you have like towns across the whole US, much bigger data set. So you don't want to bring in all these extra towns or you have no water quality data for. You only want the ones that match your data set. And that's why like a left join would be super valuable. If you wanted to throw in everything, full join would do that. So it would create NAs where there isn't, let's say, the stream quality or some of those values in those columns. Besides those are the most useful. I rarely do inner join or semi-join. Anti-join can be really helpful to figure out which stuff's missing, but it's usually only like a diagnostic for if something went wrong. Right join can be helpful too, but typically your left argument is your data frame you're kind of manipulating, and you're usually not wanting to join by the right one, but it can happen. And so just to kind of give you an example, so it kind of maybe it'll make more sense this way to talk about. Imagine you have this data set A and you have this data set B, and you have these two columns, X1, X2, in data frame A, and X1, X3, and B. And so when you're merging these two, when you're joining them, you're joining by the shared column that they have, and you specify that with the by equals argument. And so for both of these, right, they share the X1, but they don't share the X2 and X3. So what happens is they'll look for matches in the X1 and X1 in each of those. And if they match, they'll kind of append the other X2 and X2 or X3 to that join data frame. So if you're doing a left join, right, you're starting off with this A data set, and you're going to match up, say that the A and uppercase A will match. So we'll get both of those here. We'll have the X2 and X3 data there for it. B matches each, so you'll get both of those. But you'll see that since it's a left join, you're going to retain everything in the A data frame. And so you have a C, but there's no C here. And so since there's no C, we don't have values for the X3 column. So that's just going to be left as an NA. And so there's just, you'll know there's missing data there. Conversely, if you did it for the right join, right, it's going to be your missing value is like, there's no row D or value D for the X1 here. So it's just going to be an NA when you merge those two. If you did full join, right, it's going to retain all those rows, and you'll see both those NAs for C and D here. And just one more point, just to maybe drive it home. The other thing too, and sorry, I'll mention too, is that if you have, say like the C matches like 10 C's, or sorry, say like there's like 10 C's here and there's only one C here, it's going to actually copy all of those values that populate that whole, all those rows, which usually is what you want. So imagine like you have say like you have stream quality data, like you have 10 different data points at one town, and you have like a site level like temperature. So that temperature value is going to be copied and filled in everywhere. And usually that's what you want. And just to kind of drive that home, here's this kind of GIF that shows you this kind of left join with the X and Y data frames. So we're joining by this column of the red, blue, and green or purple. And so since we're doing a left join and the left one's X, it's going to merge over and keep that third row. But since that number 4 is not present in X, it's going to be dropped from the data set, the new or joined data frame. So I'll show you some examples of that. So first, I just created a dummy data set to join the two, and just, it's called climate. I'll just show you what climate looks like. And so and the original penguins data set, let me just show you, run it quickly. I'll write something, code, live coding, it'd be very exciting. So island here. This is something really helpful if you want to just see all the distinct combinations. You can run distinct after it. So I'm just going to pull out the island in years just to show you all the combinations at present. So we have 3 islands, Torgerson, Bisco, Dream, and then they're present at 2007, 2008, 2009. And so I'll do the same thing with climate, show you. Here. Distinct. And so this data set we're joining, the columns that are shared are island and year. And there's Torgerson, 2007, 2008, 2009. There's Dream, but there's no Bisco. I switched out Bisco with this other island called Christine, so we can get that kind of mismatch to show you how these different join operations go. So don't need that. And so this also has average temperature, kind of like the example I gave about towns, same idea. So just to show you it again here, the different temperatures, these will be copied over for each of the years. So with any row that matches Torgerson 2007, with like a left join, it's going to copy 3, 3, 3, 3, 3 for all of them. So here we'll do that. So we'll pipe in our data frame, our left one. And then if you hit, I'll pull up that file for it. So it's always set up as X and Y. So the X is assumed as our left one because we're piping that in, but I could write Y equals here. And this is our Y data frame, climate. And then we're going to say match them up by island and year. So when we run this, oops, did I not create? Oh no, I have to create this object before. Oops. I received it. Okay, I reran that code. It's just that summary we were working on earlier. Just a smaller data set. Okay, so now we have that. We can join by island and year. Oops. So you can see the Bisco right doesn't exist in our climate data set, but we still want to retain it because we're doing a left join, and this is our left data frame. So it's going to create NAs for those, which is fine because we know it's missing data. And then it's going to fill in the others. And then nice thing about this too is that we can pipe this into view. And when you pipe it into view, we can pull it up into this window here. And so you can see, say like we want to show you Bisco, Bisco Dream, and then we'll organize it by year. So you can see, right, Dream 2007, -3, for all of them. But Dream 2008, -4, because I copied it over. So that's how left join works. Do the same operation for here. Oh, say like if you only did one of the two, you can also run that. I believe, yes, what will end up happening, say if you didn't specify all the columns you were going to use, what it will do is it won't know how to handle the year. And so your X column, it will actually create a column called year.x. So this is our year for the left data frame. And this is our year for the Y one. And it'll actually populate each of the, so this average temperature is going to be shared across all the dream samples, right? Oh no, it'll populate extra years for each of these. So it'll kind of blow up your data set. If you can also say run it without it and it'll actually assume it. I would not recommend this, but you can do this just because you're leaving it, it's kind of risky. You don't know exactly what you're going to get. But you can see it'll give you the output of what it joined by. So you could always double check it that way. And so they'll join by those two. And I think I still have a grouping, so I might ungroup. So if you ever look at this, this means there's a grouping still ongoing. I don't think it won't interfere with join by operations. Pretty certain, but just to be safe, sure, I'll ungroup. And so full join, it will create NAs for all the ones that don't exist. And so this example, unlike the left join, right, we're going to get Christine Island to pop up in this data set now because it doesn't exist in our normal penguins, right? So see, we're missing all the penguin data, but we have the Christine data set there because we did a full join. And right join too, though, not really helpful for most stuff. So that's kind of joining two data frames. Super helpful too. And now let's move into pivoting data. But to talk about that, we should first explain what tidy data means. So for working operations in dplyr, and for most things, especially modeling in R, they typically expect you to have data set up in this form called tidy data. And what that means is it's usually what's referred to as long form, in which every observation has its own row. So a row is just one observation, one kind of data point, or yeah, set of data points. And then you can see here, and then each column are your different variables. And then within each of those, you have one value in it. So you kind of break that rule a little bit later with some of the iterations in per, but we won't get into that now. But the most important is variables and columns, observations and rows. And so this creates, and it's referred to as long form because when you do that, you end up with a lot of rows because you're, say, getting all your factors kind of split out. And so for this example, they have country, year, cases, and population. So countries, all your countries are in one row, all of your years are in one row, all of your cases, and all your population. So these are all the variables. And then so for every observation, it's a different country in a different year. And so you can see Brazil is featured in multiple rows, but remember it's Brazil in 1999. Yeah. So that's kind of how tidy data works. Often though, you're not given data that's like this. Often you're given data that's kind of a mess, and usually what's described as long form, in which you don't kind of meet these conditions. So in that case, sometimes all these like countries could be different columns, like Afghanistan, it could be here, Brazil, China, etc. And so that would make it more complicated for doing a lot of modeling later down the line. Great example of this is, imagine you have this data set here, and where your treatment is in the right form, right? You have your treatment 1 and treatment 2. But this one's really messy. You have ammonium from one sample here. For whatever this one is, maybe it's day or something. Let's just assume the underscore number of days. So you have ammonium, ammonium, ammonium here. You have multiple for nitrate and nitrite. So it's all in this kind of long form. Each of these are not each of these are not, each row is not an observation. These are all these observations across here. So we have to kind of take this form that's really wide and kind of reorient everything so then it becomes what's called long form. And there's a really easy way, and just credit, this is from Lindsay D. Brin's example on pivoting data. I'm going to throw one water related example in since most of my stuff is very biological. Apologies. So kind of we want to take this data set, and this is kind of what the form we want it to end up looking like. We want like kind of our treatment, or say sampling date, that's our first one, or say like our, and then another one, say a sample ID or replicate, all is kind of one, all these in like one column, so these variables, then all of the ammonium grouped into one column, all the nitrate values, all the nitrite values in one. So this is something, the one below, something you easily plug into like a linear model, but the top one you can't. And so the top one is kind of how it's common for people to input data that way, because it just makes sense for them there. But when you're trying to think through, it doesn't help. So every row right now is one observation of the sampling date and replicate. And so this can be easily used. So this is the bottom form, right? It's a long form. That's what the Polymer Penguin says already was in. And if it helps, here's kind of the function we'll write in R to do it. And this is kind of how it kind of will flip the data for you. So if we imagine we had this long form here where we want X, Y, and Z to be all collapsed into one column, one variable. And these are kind of their corresponding data with some ID column here. This is kind of what will happen when we do it. It's going to expand these ID columns. It's going to be a bunch of these, but now we have it. So the X, Y, and Z are now in this key, and then all these values in the middle are now in this val call. And so you can kind of do this by doing this function called pivot longer. So it used to be really confusing in dplyr because they used to have all these other ones named like spread and gather, and no one could remember which is which. But now it's just kind of simple. If you want it longer, do pivot longer. If you want it wider, do pivot wider. And so what you need to do it is you just need to fill in these kind of conditions. First, you need to give the names of all the columns in a vector, so X, Y, Z, that you're going to want to collapse into a column. Then you need to say names too, is basically you're naming what that column, that new column you're creating is called. And then you're also creating one for all the values in there, and we'll call it val. So you run this, it'll take this data frame and turn it into that data frame. Yeah. If you wanted to go, say, the other direction, long to wide, you could take this data frame here, do pivot longer. So first you pipe in your long, right? Names from equals key. So we're going to take this, expand this out, and then all the values we're going to fill in with the values from. I can never remember names to and values from, but the way to think about it is if you're doing pivot, oh, sorry, this is wrong. It should say pivot wider. Apologies, I didn't copy that over right. If you're doing pivot wider, you're taking your names, it'd be the names from and values from, because then you're expanding it out wide-wise. And then the pivot longer will be the values too, because you're now creating a column. So pivot wider, you're kind of breaking down one of the columns. Pivot longer, you're creating, so it's two. I'll give a bunch of examples. And just to kind of, if it helps you to visualize the two, this is kind of what's happening. So here's a wide form here, and then we're expanding this ID column and putting all of this into it. This they refer to as name as opposed to key, but it's the same thing. So that's kind of, if it helps to kind of visualize how the data is being moved. And you can see this is much longer, and this one's much wider. Okay, before we get to that example, let's show some pivot examples. So this is kind of the data set I think I was just showing you. So imagine we have this wide form here. So we have these ID, X, Y, and Z. And so wide looks like that. And then we want to transform it to make it long. So just like kind of it says in there, the columns we pull. So you select the columns you want to collapse into one. So X, Y, and Z. names to, and then we'll name it to key, like I said in the example, and then values to val. So if you run this, we'll flip it around. And then so now the ID has been expanded, and then we have key for all of these variables and the values stored in the val column. Conversely, I'll have to save this. So it works. Conversely, we can flip it back around using pivot wider. So then you select ID calls. So this is the columns you're using to expand. So it's, sorry, I just pulled up the longer J, so it's easy. So it's taking the ID, and then we're also, oh, is it that? Sorry, no, this is wrong. It should be key, right? No, sorry, never mind. I'm mixing myself up. ID calls, this is our ID we're taking, and then names from, these are the ones we're expanding. So the ID calls is going to keep this column, but the names from is going to expand the key one out, the values from val. Yeah, that's right. All right. Did have it right the first time. Cool. So here's just some simple examples I can give with the penguin data set too. We took the summary penguins again. We can select a few variables just for ease. So species, sex, average mass, and then say we can also then pivot it wider. So then all the different species are then specified across. So we can pivot the species, and now all the different species are now their own column. So this is no longer long form, right? Because our one variable species is now multiple columns, but maybe it's helpful for you all to read it this way. Sometimes it's nice to pivot it just to see what the data looks like, because it's hard to sometimes interpret from long form what's happening. I'm going to write all that to file because I might pull it. And then we can take that wide form right below here, and then we can pivot it back to show you. So I'm just selecting the calls again, right? And then the values to species. And I think I've got names too, but they already, yeah, if you don't specify names too, it'll just fill in names, but we can just add names too. Just put species again. One thing too to notice is, since we're creating new columns, and this is the same thing with mutate too, you put quotation marks around them when you're creating columns. If the column already exists, you don't need quotations like Adele, Chinstrap, Gentoo. Though I think you could probably run it with the quotations and it wouldn't fail. Let's see. I can't remember. Does that work? Yeah. There's no need to. Okay, and now here's for the water example. This one's trickier. So I just hand wrote the code from that table to make a data frame from it. So here's the table again that you saw from the example. To make it wider, this one's a lot trickier because you need to parse the names of them to pull out the suffix of the _1. So I'll kind of show you how to do that. Don't worry about this too much, but just in case you cared, that's how you do it. So if you pull out, it'll be calls as a column, so select all of them. So just like kind of in subsetting, you can use the colon to go from the first one to the last one. Names too, and this is where it gets tricky because we want the value to be the different nutrients we're going to pull it from. And then this is a sample for the second part. And then I'm going to do this regular expression. We'll find this pattern. So basically I'm saying there's two partitions, so you have two parentheses. It's going to pull out whatever's in here, the first one. So that dot means any character until, and then the wild card, that star means keep going until we hit this character here, which is that underscore that they all share. It's basically going to take those values and split them up into two. And all the vowels will kind of be collapsed into, yeah, I think it'd be nutrient, right? I guess it doesn't specify nutrient. Anyways, the vowels will be created into different, the different columns, that's right. So it'd be, I did the dot vowel, so you have ammonium pulled out as one, nitrate, and then nitrite too. So in case you, and then values will be some values to the concentration. So you run this, it'll create that data frame. Don't worry about this too much. It just shows you that there is a lot of functionality too if you need more complex examples, but I've only done this for this example, so I wouldn't worry too much. So cool. Now let's get to the final one. So apologies, this is another biology example, but this is kind of the data I have at hand, and I think it nice because it ties in all these examples together. So I'm going to use some actual real data from sequences of fungi that I've built with my PhD. So when we do, I have a bunch of data, and it basically is all these samples where we figured out the abundance of all these fungal species within those samples. And we usually compile it into these kind of tables where you have across your columns are the different fungal species. So here's just an example of some fungal species, not the ones in the data set, but pretty ones. And then each row is your different samples. And so it might sound like, oh, wait, this is per observation, right? Is this in long form? No, because remember, our species are all the different columns. We want to collapse all the species into one column later. So this is a great example of actually wide form data. That's kind of a pain to work with dplyr until you train. If you don't know how to use pivot longer. And then along with that, I have taxonomic information that connects all the species names with the full kind of taxonomy. So it tells you what family, order, et cetera, genus, species they all belong in. And so this is a great example of like some extra metadata that we can match up with the abundance table once we make it in long form. But right now in wide form, right, we can't merge them because there's no join column. But we will have a join column of the species name, which is what these pictures are in the data set. So I just want to, and we refer to all of these, instead of the pictures, we refer to them as OTUs, which is just a placeholder for species, since only like 5% of fungal species have been identified out of like the 5 to 8 million. There's a ton of fungi out there and a lot to be discovered. So we just have a lot of placeholder names for them. So OTU, just think of species in this example. And then, so we can ask all these kind of questions from using these two data sets. Which fungal OTU is in the most number of samples? So like how many samples are each of these fungal OTUs found? And then can we figure out which are like the most common ones? Which fungus has the greatest abundance? So just using those OTUs, can we figure out which one's the most abundant? And then what order has the greatest abundance? So then moving a broader taxonomic scale, we can then calculate that too. So I'm going to run through how I quickly kind of do all these operations in R. And so hopefully you can see, right, we're joining these two data sets. We're going to have to clean them up a bit to kind of get these kind of different things or calculate some things and then summarize it at the end. Okay. So here's the final example. So I can read in these two data sets pretty easily by using read.csv. And so if you run this command, just to show you what the kind of output will look like. Another thing I haven't talked about yet, but read CSV is also really nice because if you printed a data frame to your console, you'll find that often it will have to print the whole data frame, and sometimes that can take forever and freeze your computer. So the read CSV will import it as a tibble, which is going to be much more user-friendly, and will stop after 10 rows and number of columns too. Biggest problem is the number of columns, mostly with writing or when you send it to the console. So this is our abundance table. So ITS is the name of the samples. And then OTU and then some number are specific OTU names for each of them. So these are all different kind of fungal species. And then within this table, we have abundances. So this is how much, you can think of this as like OTU1 was really common in this sample, but it was not found in this sample. So higher number means more common, 0 means it's absent. So it's a good wide form data set. And then we can read in this taxonomy. And so I took a subset of the abundance table. So it's not the full thing, but this taxonomy is the full thing for my full data set. So it's actually a pretty big file. So you can run dim to get the dimensions for a data frame. You can see that I have the taxonomy for 6,800 OTUs. And we can kind of figure out how many OTUs we have in here, right? Oops, did I not run this? No. We can figure out how many OTUs we have in here because it's going to be the sample and then everything else is an OTU. And so we can see that there is 550 544 columns in total, so -1 for the sample, so 543. So in other words, this taxonomy is much broader than we have in our abundance table. So taking abundance wide, now let's kind of transform it or pivot it so it's in long form. So first we can start off by pulling out the columns. And I haven't talked about this yet, but with select objects, there are these what are called helper verbs with them. And so there's a lot of really cool kind of things you can kind of pull them up. So there's a lot of helpful helper verbs. So if there's like something where they all start the same, you can use starts with and then right with that string that's the same. Also ends with, contains, matches, number range. It's really helpful to grab all of them so you don't have to write every column, or use say the colon and choose the first and the very last one, which would take forever to figure out. So that's super helpful. So it's gonna leave the sample column that's labeled ITS in there because we don't want to pivot that. And then we're going to put names too and create a new column called OTU, and then a value. So it will all go to this column name abundance. So this will take it from long form and make it wide. So here you go. So we went from this super huge table now to this really skinny and long table. And so you see so the ITS1 sample is now across many different rows, but then it gives you say in ITS1, the abundance of OTU 100 is 2. And so that's super helpful. Now, because this data set has a lot of zeros in them, I could make this a much smaller data set by just filtering it. Write it on line here. We did abundance greater than 0. We can go say from a data set that's over 48,000 rows to one that's only 4,000 rows. So I would typically do that because it can be, it can make your computer slower if you start filling up the memory with these massive data frames. Oh, let's see, I do it right here too. So now that we have a pivoted table here, right? Yeah, sorry, run, right? We have this, yeah. Now that we have a table that's been pivoted, we can pull out the ones that are 0 because we don't need them. It's just kind of junk in the data frame. And then we can now start to figure out some of these questions. So to first calculate which fungal species is in the most number of samples. So we want to basically count how many different samples each fungal species is in. And anytime you're trying to think of doing any operation for like, if you're using the word each, I would clue in to you're going to want to group by whatever that variable is. So we're counting for how many samples each OTU is in, so we group by OTU. And so if we run the first few, we can see we're going to create a bunch, 543 groupings, right? As I mentioned before, how many OTUs there are. And then I did it this, so I did summarize because I wanted to kind of collapse it down because I don't really care for the abundances after that point. Because summarize is basically going to say, take all those groupings you did and calculate that one thing or one or more things with that. So n just counts how many rows for each of those OTUs. So it would be number of samples. And so see how many samples there are in a lot of these. And sweet, we get a bunch of numbers with that. Super helpful. Then we'll ungroup so we get rid of those things. Then we'll use arrange, and remember arrange just kind of moves your column or sorry, your rows around in some specific order. It typically goes from least to greatest. So what I usually do is I plug in DESC before the column of interest. And so this will go from highest to lowest. And so you can just say descend and you're arranging it by the number of samples. You could arrange by OTU, but then it would be kind of weird, man, because it'll be kind of like arranging in, I forget what the equivalent in Excel is, but you know, like when you do that with text and numbers, it kind of arranges it kind of like this, where it's 1 is not 2, but then like 1, 1, 0, 0. Anyways, so you can run this. You can see there's no grouping anymore because I got rid of it with ungroup. And you can see OTU once and the most number of samples, OTU 26 and the second most, etc. And if you want to only keep the first 10 rows, you can use a function called slice. And slice will just allow you to select which rows you want to keep. So kind of a slice will allow you to then keep the first rows 1 through 10 in this example. So we'll pull those out. And then so these are the most common ones. And then just for fun, I can do left join with the taxonomy, match it up by OTU, because remember this is what is shared across the 2 days. That's the OTU column. And then get the full kind of taxonomy of that OTU, just for fun, just to see who they are. And so as you can imagine, most of them are unknown, which is super exciting and somewhat frustrating, but it gives you just somewhat of an idea of who the common ones are. So a lot of Ascomycetes. So cool. So we found which fungal species most number of samples. It's OTU1 and OTU26. And it's a Nectriaceae, probably something closer related to Fusarium, if you know what that is. Next, which fungus has the greatest abundance? So if we were trying to figure out the abundances of each of these, instead of doing like the N operation to count the number of rows, now we're going to kind of do kind of the same pipeline, but instead we're going to sum the abundances. So let's look at the total abundances across each of the OTUs. So you can kind of run the same thing, same way. So virtually the only thing that differs in the two pipelines. And now you see that there's other ones that are more abundant, like OTU16, and it's in Heliotales. So what's really cool is like we did a totally different operation, but all we had to do was change what we were summarizing by. And that just kind of shows you how quickly you can kind of pivot and, or not, sorry, pivot's not a helpful word, how quickly you can kind of tinker with these kind of pipelines and create some very other or very different kind of analysis. And shows you just kind of the genius of having these composable pieces. Finally, we can calculate what is the order of fungi that has the greatest abundance. So since we're no longer thinking about individual like OTUs, now we're going to think about grouping by order instead. And since we need, say, the taxonomic information earlier on to group by that, we'll have to then join our taxonomy data frame up here. And just since I didn't mention it before, remember, since the taxonomy table is massive and there's a lot of data in there we don't need, we'll use left join because we only want to pull out the taxonomy that matches our current abundance table. So we'll just run these first few lines. You can see it's going to populate this taxonomy for every OTU and its abundance in each sample. So it's going to create, the taxonomy is going to be copied a bunch of times. So I can kind of show you this. So if you organize it by OTU, right, you can see OTU1 and all the taxonomy copied for every sample the OTU1 is present in. And so we're going to group by this, so by the order. So it'll be 53 different orders that we'll be calculating it for. Then we're doing the same thing before of just adding up the number of reads, or the abundance, sorry. And then so now we have a simplified, remember, like when we summarize, it's going to be the group by and what you're calculating is what will be returned. So since we're only grouping by order, we'll get that, and the number of reads, a new column we create by summing up the abundances of each of the orders. And so here is the most common, same thing before, we can do ungroup to remove that. One thing you'll notice, and I chose to do, is actually filter out this column called for the order that is unknown. And so this is another one of those conditional operations that says not unknown. So it's going to return everything but this unknown column. So just removing that for make it simple. We'll arrange by descending order the number of reads. And then we'll just take the top 10 by using slice. And there you go. So the top orders are Heliotales, Hypocreales, and Christophibliobsidales. Super cool. So Garicales, the one that most of you are probably familiar with, your common mushrooms. It's actually not the most common one in the data set. So that's interesting. Cool. So that answers all the questions. And just for fun, here are pictures of Uloshiales. These are what they look like. So that's kind of working through Tidyverse. As I said in the other video too, let me know if you have questions, concerns. Feel free to email me. Feel free to message me on Slack. I can help you run through or clarify anything I mentioned in this video. And thanks.